Okay, hello ladies. Today we are on page 36 of your packet, and we're going to work through this table to compare and contrast the two classes of genes that regulate the cell cycle. This table just really summarizes the information from the videos that we did from the NIH on page 32 of your packet, animations 1, 2, 3, and 1 through 5 regarding the genes that control the cell cycle. So if you don't have one out now, could you go and grab a red pen and or a red marker or a green pen and a green marker? So if you need to go do that, you can just hit the pause button and then come back. Okay, so we're going to compare and contrast the two major classes. That's why we have two columns here. So the first class of genes is called proto-oncogenes. And some of the sections of biology went to the purple section in their binder. So if we did not do that yet, go to the purple section of your binder and write onco in there. So again, if you need to pause the video, go ahead and do that now. Okay, so hopefully we're in that purple section. So go ahead and write O-N-C-O, onco, and then the meaning is cancer. So we'll fill that in, and then while you're in the purple section, we might as well do another one. Let's do dash O-M-A, O-M-A, as in oma, as in carcinoma, melanoma. So OMA also means cancer. And then we'll go ahead and flip back to page 36 of your packet. Okay, so we have two classes of genes that regulate the cell cycle, proto-oncogenes as well as tumor suppressor genes. And I wrote this one in green because proto-oncogenes tell the cell to go through the cell cycle and promote cell division. And I put tumor suppressors in red because they stop cell division, they prevent cell division. So let's go ahead and fill in the normal function. Proto-oncogenes promote cell division. So proto-oncogenes code for proteins that tell the cell, go ahead, move through the cell cycle. And the way I remember that is just proto-oncogenes begins with pro and so does promote. Okay, I also want you to know here, even though it has the root onco in it, proto-oncogenes are not cancer genes, they are normal genes. And then the tumor suppressor, by contrast, they inhibit or suppress cell division. So think of inhibit as to slow down or prevent or suppress. So you need to know all of those words, that inhibit is the same thing as suppress or prevent. Okay, and then I like to use a visual model to help my brain understand what a proto-oncogene is and how its function matches its name. So we're going to use a green light, like on a traffic light, to represent proto-oncogenes. Or if you don't like that analogy, we can use a green up arrow. Both of those say, go ahead, traffic can flow, or go ahead, increase the number of cells. On the other hand, tumor suppressor genes can be modeled with a stop sign. So go ahead and draw an octagon in red. Or alternatively, you could use a red down arrow. And just kind of be careful of maybe the size of the green arrow in proto-oncogenes. Okay, so I also like to use an analogy for helping our brains to understand what a proto-oncogene is. So just like your car knows how to stop and how to go, so we can use kind of that car analogy again for the cell cycle. So you can think of proto-oncogenes as coding for proteins that are kind of like the gas pedal or the accelerator in a car. So the accelerator pedal is the one on the right. So when you push your foot down on the accelerator, your car will move, it will go. It tells the cell, go ahead, move through cell division. We can compare that to tumor suppressor genes, and they kind of stop your car. So it's like putting your foot on the brake of in your car. I know you guys aren't old enough to drive yet, but most of you have been at the bumper cars. Okay, so just like any gene has the has the capacity to be mutated, and again, mutations are just changes in DNA. When they get mutated in a certain way, they can become what's called oncogenes. So protooncogenes are the normal version of the gene, and then oncogenes literally means cancer gene. So a proto-oncogene can get mutated to become an oncogene, and this is what you don't want. Okay, now we don't have a new name for tumor suppressor genes when they get mutated. We just call them mutated tumor suppressor genes. Okay, so let's go ahead and kind of modify the model to represent that there's been a mutation. So in fact, you can draw a thick line right here where the arrow or the pointer is tracing right here to kind of show that what's going on in this part of the table is different from what's going on in the bottom part of the table. So one of the other classes this week, instead of drawing a green arrow, a green traffic light, they drew lots of green lights. Or you could think of it as the green light always being stuck in the on position. So maybe you want to draw a bigger green traffic light or more green traffic lights, something along those lines. Alternatively, if you like the arrow model of a proto-oncogene, you can just draw a much larger big green arrow in the mutated section than you did up here. All right, so what happens when tumor suppressor genes get mutated? Well, it's like the stop sign not being present, or like someone took the stop sign down. So you can imagine a car accident would occur if there's no stop sign at an intersection. Or you could think of a smaller red down arrow or no red down arrow at all. So you can understand that there would be a car accident if either of these mutations took place. Either the traffic is moving when it shouldn't be, so maybe the green light is on for both directions of traffic at an intersection, or there's no red light coming on, or there's no stop sign. There would be, and there should be. Okay, so if we mutate our car analogy up here, it's like the gas pedal staying depressed and staying on when you're not pushing it. So if you were to take your foot off of the accelerator, off of the gas pedal here, the gas pedal would stay depressed or stay pushed down to the bottom of the car. So that's not good. You don't want the gas pedal to be on. You don't want the cell to move to the next cell of the cell cycle, the next stage of the cell cycle. So this is not a good situation. Alternatively, if we mutate tumor suppressor genes, it's like the brakes failing. So you're depressing the brakes and the car is not stopping. And you've probably all seen that in a movie in some point, and that's not a good sign. You want the car to go when you want it to go. You want it not to go when you don't want it to go, and you want the car to stop. So what is the effect on the cell? What happens when there's a lot of mutations in proto-oncogenes and tumor suppressor genes is that we have uncontrolled cell division. So it's kind of like someone saying, go ahead, go through the traffic when you shouldn't. Well, that can lead to an accident. And the same thing with tumor suppressor genes. If someone's brakes are failing, there's going to be a car accident. You're going to have uncontrolled cell division. That's not good. So you're getting too many cells. And remember, cancer is just uncontrolled cell growth or uncontrolled cell division. I guess cell division is more appropriate than cell growth. It's not the cell getting larger. So both of these lead to cancer, and usually it's an accumulation of mutations. So it usually isn't just one proto-oncogene is mutated or one tumor suppressor gene is mutated. It's often that there's an accumulation of mutations in proto-oncogenes and tumor suppressor genes, and there's lots of proto-oncogenes and tumor suppressor genes. So It's kind of like you could think of a newborn or a child hasn't had much exposure to ultraviolet radiation. Um, and so they don't get cancer. They haven't had a lot of time for mutations to accumulate. But older people have had more time to be exposed to UV radiation, and so they've accumulated the mutations over time. So it's often that accumulation that leads to uncontrolled cell division. And if so, that's our two classes of genes: proto-oncogenes and tumor suppressor genes. And remember, they encode proteins that are responsible for the cell cycle. And there are lots and lots of proteins responsible for controlling the cell cycle. If you see all these little jelly beans right here, every time you see a little color, that's a protein that's responsible for moving the cell from, say, G1 into the S phase, into then the G2, and then proteins involved in controlling mitosis. So you can see all these little jelly beans are proteins that are responsible for making sure the cell is okay. Shadow, I will let you out. Stop scratching at the door. Okay, so I believe that's all I have. If you have questions about those two types of genes or anything about that table, feel free to email me.